Lecture 3: Text and Gesture Interaction. Guest lecturer Per Olaf Christensen will present this idea using a case study based on his own recent research, leading to a successful product, recent buyout, and extensive press coverage. When technical people are commenting on or even creating user interface, they often get distracted or hung up on the hardware used for input and output. This is a sign that they haven't thought very hard about what is going on underneath, and also that they will never keep up with new technical advance. There have always been good and bad examples of interface design using control panels, punch card, teletype, text terminal, bitmap display, like pen, table, mice, touchscreen, and so on. With every generation, you can hear people debating whether, for example, the mouse is better than a touchscreen or voice input is better than a keyboard. Debates like this demonstrate only that those involved haven't been able to see past the surface appearance and the marketing spiel of the device manufacturer. An opinion or expertise on this matter quickly get out of date. Within the past few weeks, I heard a leading researcher tell his sponsor that we have added a GUI to our prototype, as if that was an important thing. 20 years ago, it was something of achievement to get some output on a bitmap display rather than a command line text application. Nowadays, it's more challenging to work with projection, surface, and augmented reality, more of in the later lecture. But sensing and display technologies change fast, and it's more important to understand the principle of interaction than the detail of specific interaction device. The lecture on visual representation was based on display principles that are independent of any particular display hardware. If we consider an interaction principle that are independent of any particular hardware, these are: how does the user get content, both data and structure, into digital form? How does the user navigate around the content? How does the user manipulate the content, restricting, revising, replacing? These are often interdependent, and the data system for the text entry presents an interface in which the user navigates through a space of possible text as predicted by a probabilistic language model. So it can be considered both as content creation and navigation. It is relatively hard to structure and revise text using Dasher because the language model only uses a 5-character context, and many text documents have structure on the large scale than that. However, this provides an excellent example of an interaction paradigm that is independent of any particular hardware. It can be controlled using mouse, keys, voice, breath, eye tracking, and many other devices. The general principle, direct manipulation, and interface models. At the point where GUI was about to become popular, HCI researcher Ben Schneiderman summarized the important opportunities it provides under the name direct manipulation. In fact, some of these things were already possible with text interface. For example, after the advent of full-screen text editor, they remain relevant in more recent generations of hardware. It is also possible to use GUI libraries to create bad user interface that do not support this principle. Just being graphical does not make it good. The principle of direct manipulation as described by Schneiderman are an object that is interest to the user should be continuously visible in the form of the graphical representation on the screen. Operation on objects should involve a physical action, using a pointing device to manipulate a graphical representation, instead of command with complex syntax. The action that the user makes should be rapid, should offer incremental change over the previous situation, and should be reversible. The effect of action should immediately be visible so that the user knows what has happened. There should be models set the command doing everything that novice might need, but it should be possible to expand this, gaining access to more functions as the user develops expertise. We should also note an additional principle defined around the same time by Larry Tesler and Apple, that the same action should always have the same effect. It's hard to believe that will not be done, but I was championing against editor like V, which many people found unusable because hitting the key on the keyboard could be different consequences at different times. Tesla campaigned against modus in the user interface based on his studies of non-technical users. Search for no modus to learn more. The large achievement of the Windows style interface is that the frame around each application gives the user a clue about different models. But as Tesla said, removing modus altogether is great ambition. Context creation. Text context. Guest lecture will discuss this, including how we can assess and measure the efficiency of alternative text entry mechanism. Non-text context. This course will say very much about non-text context creation. Content can cover the music, visual art, film, game, novel, and many other genres. To understand any of them well, you will have to take a degree in the relevant discipline, some available in Cambridge. All of field develop their own professional tool, and there is constant stream of the amateur tool model on the professional one. Cultural tastes don't change the fast. The rate of the change is generational, not annual. So digital content creation tools is usually different from an immediate the artistic tool of previous use. Generation, camera, microphone, mixing decks, typewriters, innovative content creation tool appear first in the avant-garde contemporary art and take a generation to reach popular audience, get taken up by mainstream professional artists, and become subject to consumer demand for amateur tools. For example, sampling and mashup were first explored in the mid 20th century by music concert. Composer using tape recorder. The Computer Lab Rainbow Group has always had an active program of the research engagement with contemporary artists developing new digital media tools. The research continues actively at present, but outside the scope of an introduction to HCI. Content manipulation and navigation via DXs. In order to manipulate content, the user has to be able to refer to specific part of the product, whether text, diagram, video, audio, that he or she is working on. In early text interface, references were made by numbering the line of the text file. Each substitute Fred for VRD or online 27 s /VRD /Fred / as in programming language line number could be replaced by label, but it's irritating to give everything names. Imagine a shop where everything for sale was given its own unique name, or had to be referred by index position of aisles, shelf, and item. It's much easier just to point and say, I want the one, I want that one, in the language. This is called basis sentence, in which the object is identified by pointing at it, rather than by naming it. For the same reason, basis has become universal in the computer language, and this is why devices for pointing are so important in user interface. In early GUIs, the combination of mouse and pointer to achieve the axis was a significant invention. Hence, the web interface, Windows icon, mouse pointer. Other inventions around the same time were the placement of the text cursor between characters rather than identifying a single character. Larry Tesler had a hand in this invention too, but new hardware suggests new approaches to DXs. Touchscreen, augmented reality will require new invention. It's reasonable to assume that DXs in different media can be achieved in different ways too. Audio interface, camera, and other devices do not necessarily need to have a cursor. In many cases, what they require is they take methods that relate user gesture, detect via any kind of sensing device with a media location, navigation, and is then a matter of supporting user strategies to vary that location, including technique to show local detail within a larger context via scroll bar, zooming, thumbnail, fisheye view, overview map, structure navigation, and so on. Simple context manipulation includes simply adding more context, perhaps inserted within a particular context, or removing content that isn't required. Anything more complex involves modifying the structure of the context. This is an area which user interface design can build on insight from the usability of programming language in a later lecture. Evaluation of pointing device and WIM interface. As with lecture N3, modern user interface involves so much pointing that it is worth optimizing. The efficiency of the interaction. Early HCI models based their optimizing on the Fitts law and experimental observation that the time it takes a point at a given location is related to the size of the target and also the distance from the current hand point position to the target. Fitts' original experiment involved two targets of variable size and separated by a variable distance. Experimental subjects were required to touch first one target, then the other as quickly as they could. The time that it takes to do this increased with the amplitude of the movement, a distance between the target, and decreased with the width of the target that they were pointing to. T equals k log 2 a slash w plus 1, where a equals amplitude, w equals width. When evaluating new pointing device, it can be useful experimentally to measure performance over a range of the target size and motion distance in order to establish the value of the content in this equation, sometimes called ID, the index of difficulty. In user interface, they require a user to make many sequences of repetitive action. For example, people working in the telephone call center or in data entry. It can be useful to compare alternative design by counting the individual action needed to carry out a particular task, including the number and extent of most motion, as well as all the key pressed on the keyboard. This keystroke level model can be used to provide quantitative estimates of user performance and to optimize the design and layout of the interaction sequence. It is more difficult to make numerical comparison of user interface in case where the user action is less predictable. The GOMS model or goals operator method selection combines keystroke level estimate of the user action with an AE planning model derived from the 1969 work the Ernst and Newell on the generalist problem solver. The GPS operates in the search space characterized by a possible intermediate state between some initial state and goal state. Problem solving consisted of finding a series of operations that would eventually reach the goal state. This involved recursive application of two heuristics. A. Select an intermediate goal that will reduce the difference between the current state and desired state, and B. If there are no operation to achieve that goal directly, decompose it into sub-goal until the leaf of the sub-goal hierarchy be achieved by individual keystroke or mouse movement. For future reading on KLM and GOMS, see Chapter 4 in the Carol by Bonnie Jones. Once we can measure interaction efficiency, whether text entry or time to point at the target, is possible to compare alternative design through controlled experiment with human particular. These are described in a later lecture. Lecture 4 in Inference. Mental model, what the user inference about the system. Don Norman, one of the first generation of cognitive scientists, investigation HCI also wrote the first popular book on the topic, The Design of Everyday Things. What most people remember about this book is the example of the door handle that are so badly designed they need label telling you to pull them. But his key message was to draw attention to the goal of evaluation and the goal of execution. How does the user know what the system is doing, and how do they know what they need to do in order to achieve their goal? For a review a normal models, see Action 3.3.2 in the Sharp, Roger and Price. Computer systems are so complex that nobody really knows what is happening inside, except possible the designer. In the face incomplete information, the goal of evaluation is unavoidable. The user has to make inference or guess what is happening inside. The user conclusion form a meta-model of the system. One way of thinking about the design problem is that the designer must give sufficient clue to the user to support that inference process and help the user form an accurate or at least adequate mental model. The idea of visual metaphor is that the screen display simulates some more familiar real-world object, and the user mental model will then be understood by analogy to the real world. The metaphor or analogy approach can potentially help with the goal of execution too. If the system behaves exactly like the real world object depicted, when the user would know exactly what to do with them. In practice, computer systems never behave exactly like real world object, and difference can the system even more confusing. Why do you have window in your desktop? Why do I have to put my USB driver in rubbish before unplugging? Furthermore, designer inadvertently created metaphors that correspond very well to their own understanding of the internal behavior of the system, but the user should not be expected to know as much as designer. User study can help to identify what users actually know, what they need to know, and how they interpret prototype display. Mental model research. Mental model research attempts to describe the structure of the mental representation that people use for everyday reasoning and problem solving. Common mental models of everyday situations are often quite different from scientific description of the same phenomena. They might be adequate for basic problem solving, but break down in unusual situations. For example, many people imagine electric as being like a fluid flowing through the circuit. When electrical wiring was first installed in house, it appeared very similar to gas or water reticulation, including valves to turn the flow on and off, and hoses to direct the flow into an appliance. Many people extended this analogy and believe that the electrical would leak out of the light socket if they were left without a light bulb. This mental model did not cause any serious problem. Mental model did not cause any serious problem. People simple made sure that there were light bulb in the socket, and they had no trouble operating electrical device on the basis of their model. The psychology nature of unofficial but useful mental model was described in the 1970s, and this idea has been widely applied to computer systems. Young study of calculator user in 1981 found the user generally had some cover story which explained to their satisfaction what happened inside the device. Pine carried out a more recent study of at ATM user, demonstrating that even though they have never been given explicit instruction about the operation of the ATM network, they have they do have defined mental model of data flow through the network, as well as clear belief about information such as the location their account detail. The basic claim of model theory is that if you know the user belief about the system that they are using, you can predict their behavior. The user mental model allows them to make inference about the result of their action by process of mental simulation. The user imagines the effect of his or her action before committing to a physical action on the device. This mental simulation process is used to predict the effect of action in accordance with mental model, and support planning of the future action through inference on the mental models. Where the model is complete and the user encounters situations that cannot be explained by mental model, this inference will usually rely an analogy to another device that the user already knows. Think a lot studies. A great deal of cognitive psychology research, including some basic research on mental model, has been based on think a lot studies, in which subjects are asked to carry out some tasks while talking as continuously possible. The data are collected in the form of a verbal protocol, normally transcribed from a tape recording so that subtle points are not missed. Use of this technique requires some care. It can be difficult to get subject to think aloud, and some method of doing so can be bias the experimental data. A detailed discussion of this kind of study is provided by Erickson and Simon 1985. For description of think aloud technique, see section 7.6.2 in Sharp, Roger and Price. Performance model of user. Early HCI research were largely concerned with the performance of user measured in engineering terms as the system component. Cognitive psychology is closely associated with artificial intelligence, investigating human performance by simulating it with machine. One of most famous findings in cognitive psychology research, and the one most often known the user interface developer, is an observation by George Miller in 1956. Miller generalized from a number of studies finding that people can recall somewhere between 5 and 9 things at one time, usually referred to as 7 plus or minus 2. Surprisingly, this number always seems to be about the same, regardless of what the things are. It applies to individual digit and letter, meaning that it would be very difficult to remember 25 letters. However, if the letters are arranged into five letter word, apple, grape, we have no trouble remembering them. We can even remember 5 simple sentences reasonably easily. Miller called this unit of short-term memory chunk. It is rather more difficult to define a chunk than to make an observation, but it clearly has something to do with how we can interpret the information. This is often relevant in user interface. A user may be able to remember a sequence of 7 meaningful operations but will be unable to remember them if they seem to be an arbitrary combination of small elements. Short-term memory is also very different from long-term memory. Everything we know, learning is the process of encoding information from the short-term memory into long-term memory, where it appears to be stored by associating with the other thing we already know. Current models of long-term memory are largely based on connectionist theories. We recall things a result of activation from related nodes in the network. According to this model, we can improve learning and retrieval by providing rich association, many related connections. This is exploited in the user interface that mimic either real-world situation or other family application. A further subtlety of human memory is that the information stored is not always verbal. So the memory experimental involving recall of the least violent to investigate the way that we remember visual as seen. Visual working memory is in fact independent of verbal short-term memory, and this can be exploited in mnemonic technique, which associate imaging with item to be remembered. Display icon combined with associate label provide this kind of dual coding. Intelligence interface, what the system infers about the user. A future inference problem is that in addition to the user not knowing what is happening inside the system does not know what is happening inside the user. Advanced systems can be designed to record and observe user interaction and on the basis of the data make inference about the user intent to do next and present shortcut usability queue or other aids. This kind of intelligence user interface are becoming more common, but they can also introduce several usability problems. A notorious early example was Microsoft Word Clippy, which analyzed pictures of the document and overlaid to help with anatomic formatting. You appear to be writing a letter. Although some users found it useful, a far large number found the tone patronizing and automated.